Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over ionization energies and how to interpret and understand successive ionization energies that you are given. So let's get into this. All right, so in this problem, we're given below are the ionization energies for calcium. So here are the successive ionization energies for calcium. So we start with calcium atom, and that loses one electron to form the calcium plus ion and one electron. And they give you the ionization energy. This is the first ionization energy, which is 590 kilojoules per mole. And then they give you the ionization, the second ionization of calcium. So you start with the calcium ion plus charge, loses another electron to form a 2 plus charge. And so the ionization energy for that second electron to be removed is 1150 kilojoules per mole. The third one, you're removing a third electron. So from the 2 plus ion, you're going to remove a third electron. That's going to create a 3 plus charge on the ion, losing another electron. And that requires 4,910 kilojoules per mole. And then finally, we're going to take the fourth electron. So we're going to take the calcium 3 plus ion, remove another electron to form the 4 plus ion, and the energy required to do that is 6,490 kilojoules per mole. So these are successive ionization energies, meaning that the energy that is required to remove each electron one after another. And so here are the questions we're being asked. A, explain the general trend that is observed. And B, explain the unusual large increase in the energy between the ionization energy number 2 and number 3, the second and third ionization energies in terms of electron configurations. Okay, so let us start with A. So explain the general trend that is observed. So what do we notice in the general trend? So basically, as you can see, the successive ionization energies are increasing. So if you remove the first electron, it's a relatively little amount of energy. But as you remove each electron after, the amount of energy required to remove that next electron is higher than the previous one. So why is that? Well, here I have an orbital diagram to help explain clearly what's going on. So remember, you removing electrons from the easiest to the hardest, right? What does that mean? So when I put in a certain amount of energy, the first electron to be removed is the one that's less strongly held onto by the atom. What does that mean? The negative electrons in your atom are feeling a pull by the positive nucleus. So the nucleus here being positive is attracting the electrons that are negative. So by Coulomb's law, there's a certain force of attraction between the nucleus and the electrons. But also by Coulomb's law, there's also repulsive forces between or among the electrons themselves because they have the same charge. So negative charges repel, and positive charge and negative charge, opposite charges, are going to attract. So as you can see here, remember that the inner core electrons act as kind of a shield from the nucleus. They are shielding the nucleus from the outermost electrons, the valence shell. So because of the repelling forces on the between the electrons, so the repelling forces act as kind of a shielding, and they kind of shield the positive attractive force of the nucleus from the outer electrons. The electrons in the valence shell, so these two electrons, they also apply a repelling force as well, and they have a little bit that causes a little bit of shielding as well, but not as much as the inner core electrons. Okay, so that's a good overview of what we're thinking about here. Now, why, if we think about this in terms of the how strong the attractive force is uh, on the electrons from the nucleus, and understanding that the stronger the force, the stronger the pull that the electron feels, the more energy that's required to remove that electron. So when we put in energy, the farther you get away from the nucleus, the less the force is that the nucleus is exerting on the electrons. So the electrons closest to the nucleus are going to feel a greater force of attraction because of Coulomb's law. The farther you get away from the nucleus, the weaker that attractive force is. So based on that, we would expect the electrons in the outermost shell to feel the least amount of force by the nucleus. And so therefore, removing the electron, the first electron from the outer shell, is going to be the easiest and therefore require the least amount of energy. So that would explain why the first ionization energy is the least amount of all the energies that we have. And then next you'll see that it increases here to here. So why does it take more energy for the second electron to be removed compared to the first? Well, what I said earlier was when you remove what I said earlier was the electrons, because they all have negative charges, they're all going to repel each other, and the repelling forces of the electrons counterbalance the attractive force of the nucleus. So if I remove a negative electron, that's removing negative charge, and therefore that's going to relieve or remove some of the repelling forces, and therefore that's going to allow the nucleus to have a stronger attractive force on the rest of the electrons. So then when you remove the second electron from the outermost shell, that electron, even though it's in the same shell, will still feel a greater pull by the nucleus because you've removed some of the repelling forces from the mix when you remove that first electron. Okay, so then this electron, the second electron, will require more energy to remove that electron, because that electron is feeling a greater force than the first electron is. Now, if you remove the first two electrons, then now this outer shell is empty. Now you're going to go to the next shell, and then you're going to remove the third electron from the next shell. So the next shell, the easiest electrons are going to be from this shell here, because you've already removed these two. So now you're going to remove electrons from the next shell down. And so if you remove any of these electrons, again, because you've removed two electrons, that's going to reduce the amount of attractive force. And also, that's going to reduce the amount of repelling force and therefore allow the electrons to feel a greater pull. But not only that, but notice that we are closer to the nucleus. Remember, the closer you are to the nucleus, the stronger the attractive force felt by the electrons from the nucleus. So this third electron I'm going to be removing here, that electron is going to require even more energy than the first two. And so you'll see that here as well. And the same thing with the fourth one. So I'm going to remove the fourth electron from this second shell here. And again, because I've removed three electrons, I'm removing repelling forces, and therefore they're going to feel a stronger pull by the nucleus. And so that explains why you get an increase in the successive ionization energies as you remove electrons from the atom. So I think that's a good full explanation for part A. Let's talk about part B. So explain the unusually large increase in energy between the second and third ionization energies. That means, why does it take a comparatively much more, a larger amount of energy to remove that third electron than the second, then compared to the other successive electrons that you're removing? So what do we mean by that? Well, look here. Excuse me. So if you compare the increase in energy when you remove the first and the second electrons, you'll notice that the amount of energy needed to remove the second electron is about double what it took of the first. Okay, so it doubled in size. So you need twice as much energy to remove the second electron than you do the first. If you look at 3 and 4, the third and fourth electron, you'll see that the amount of energy needed to remove the third electron compared to the fourth electron, you'll see that the difference here is not even double, right? So you might see it takes about one and a half times the energy to remove the fourth electron compared to the third. But now look at this here. Look at the increase in the amount of energy needed to remove the third electron compared to the second. It's almost about 4 or 5 times the amount, right? So this is about 4 or 5 times the difference. This is about double the amount. And the difference in here is about 1.5 times as great. So why is there such a large jump in energy needed to remove the electrons when you're going from the second to the third? Well, we were kind of touching on that in the picture here. So you'll notice that we have the core electrons here in the lower energy levels. And you'll notice that the first 2 electrons are in the valence shell farthest from the nucleus. So because the energy level, this outer energy level, is farther from the nucleus than the others, that distance makes it easier to remove these first 2 electrons compared to the inner ones. So once I remove the first electron and the second electrons, but then the third electron, right, I am now in an energy level that is closer to the nucleus. So the electrons in this shell are going to be feeling a much higher attractive force from the nucleus compared to the valence shell. So going from the valence shell to the next shell in the core electrons, that explains why you get such a large jump in the energy needed to remove the electron, because you're going from your last valence electron to the next one being taken is your first core electron. So anytime you jump from one energy level, your last electron in one energy level, to the next electron or your first electron in the next energy level below, there's always going to be a relatively much larger gap in the energy needed to remove the electron than compared to removing electrons that are in the same shell, right? So I hope that makes sense. So that is how we explain it using the Bohr model. But of course, they're asking, well, what about electron configurations? Well, let's look at the electron configuration. So the electron configuration for calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So from the electron configuration, you can see that the energy levels, the shells 1, 2, 3, and 4, right? So this would be 1, 2, 3, and 4. So you could see your valence shell is always represented by the largest number. So the largest number is 4. So anything that has a 4 is in the valence shell. So here you have 4s1. So this is in the sublevel S of the fourth energy level, and you've got 2 electrons in this energy level and the sublevel. So these would be your valence electrons. So the first 2 electrons that you remove are going to be these. And then when you remove those, now the next is the third energy level. And so now you're in a lower energy level, which means that you're closer to the nucleus. So now you've got 8 electrons in the third energy level. So now you're going to start removing electrons from there. So the third electron now is coming from the third energy level, which is closer to the nucleus. And so I hope this helps. If this helps, if you enjoyed this video, if this helped explain everything for you, then by all means, like the video, share the video, hit that like button over there somewhere. Also, do me a favor, subscribe to my channel, help me out. Click on that notification bell. When you do, make sure you click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or a question you need help with, I would love to help you with that. If you have a topic you want me to cover, let me know what it is. I'd like to do that too. Thanks for joining me and have a great day.